Okay, welcome to the next chapter in AP Calculus. So, in this problem here, we're given a graph of the particle's motion. We have the x-axis as seconds and the y-axis as being measured in centimeters, and we're asked to find these three things about the function. So in part A, we're asked first of all to find the units of f prime of x. Now that's just going to be the units for x, the units for y over the units for x. The units for y are centimeters. The units for x are seconds. So this is the centimeters per second. This is the units of our derivative. And then for the inverse of x, f negative 1 of x. So when you are looking at f of x, right, we're mapping seconds to centimeters. Our x value that's being inputted is seconds, and we're outputting a value in centimeters. For the inverse of x, it's going to do the exact opposite as you'd expect. It's going to input a value in centimeters and output a value in seconds. And those output values, what we want, that's the units of the inverse. So this is the units of f inverse of x, because this is what it's going to output. It's going to output a value in seconds. And then for the derivative of the inverse, so remember how up here the units of our derivative was centimeters per second? Well, when we're looking at the derivative of the inverse, it's just going to be this, but flipped. So the derivative of the inverse is going to be measured in seconds per centimeter, right? Okay, and then now let's move on to part B, and then we're asked to interpret the meaning of these three equations. So for the first one, the derivative of 0.420 is 0.9131. So what that means is the rate of change, right? The derivative is just measuring the rate of change at a certain input. So at 0.42 seconds, right, at this value, the position is changing, right? Because this is the input, we're outputting centimeters per second, so we're finding how quickly the distance in centimeters is changing. So the distance is changing at 0.9131 centimeters per second. Okay. And then the inverse of 0.69 is equal to this. And what this means, remember, our inverse, it inputs a value in centimeters and it outputs a value in seconds. So at 0.69 seconds, or no, not seconds, at 0.69 centimeters, right, because we're inputting centimeters, the time is 0.7615 seconds. Okay, so I'm just going to separate this. Okay, and then for part C, or not part C, but like the third part, we're looking at this. And then remember how it's going to be in seconds per centimeter, and we're still going to be inputting a value in centimeters like we always are. So this is going to be a value in centimeters, right? So at 0.5 centimeters, and then it's the time is what's changing, right? We're seeing how quickly time is changing with respect to distance. So the time is changing at 1.1547 seconds per centimeter. And that is question 1. Okay, so in question 2, we're asked to find the derivative of each of these three functions. So let's look at part A. The first thing we notice is that since there's an x and a y, we're going to have to differentiate this implicitly. So since we're differentiating with respect to x, the 2x part is going to be normal. It's just going to be 2 plus, and then for the y part, we're going to differentiate it. We're still going to say 2y, but then since we're differentiating it with respect to x, we need to add a dy dx on the end. Equals, and then the derivative of this constant is 0. Don't be fooled by the pi. Don't bring the pi down and subtract 1, because this whole thing is just a number. It's about like 9 point whatever. So just the derivative of a number is always 0. Okay, so now we have this. We're solving for dy dx, right? So we just need to solve this equation for dy dx. I can divide both sides by 2. So 1 plus y dy dx equals 0. Subtract 1 from both sides. Y dy dx equals -1. And then divide both sides by y. Dy dx is equal to -1 over y. And there is my answer for part A. And then, let's work over here. For part B, the derivative of log base 2 of the inverse secant of x. So 2 things to remember. The derivative of the inverse secant of x is 1 over the absolute value of x times the square root of x squared minus 1. And then the derivative of log base a of x is 1 over x times the natural log of a. So we need to put these two things together to get our final answer. What we're going to say is, so the outside function is the log, right? So we're going to say, okay, we're going to have 1 over the inverse secant of x times the natural log of 2, right? Because 2 is our base. Here we have log base 2. And then we need to multiply this by the derivative of inverse secant, which is 1 over the absolute value of x times the square root of x squared minus 1. And we're multiplying it by this derivative because this is the chain rule. We did the outside function, now we're moving on to the inside function. So this is our second derivative, right? We used the chain rule, and then we used these two tidbits of information to get that. And now let's do part C, e to the x times 3 to the x. This is just going to be a simple application of the product rule. So first we're going to have e to the x times the derivative of 3 to the x, which is going to be 3 to the x times the natural log of 3, right? The derivative of 3 to the x is just going to be that times the natural log of this, plus 3 to the x times the derivative of e to the x. And remember, e to the x is a really, really awesome special function. Its derivative is itself, so that's just going to be e to the x. And I can simplify this if I wanted to, and I can say this is equal to the natural log of 3 plus 1 times e to the x 3 to the x. And that was a pretty simple question, question 2. Okay, question 3. This is going to be a pretty quick one. So, we're given that f of x and g of x are inverse functions, and we're supposed to determine g prime of 2. So to solve this question, you need to know the formula for derivatives of inverse functions, and that's if f of a equals b, then f prime of a is equal to 1 over g prime of b. Okay? I can solve this equation for g prime of b because that's what we're looking for. And I can say g prime of b is equal to 1 over f prime of a. And so we want to find g prime of 2, right? So we need to find what? So we need to find g prime of 2, and that's 1 over f prime of what? So we can see here that 9 and 2, they map to each other, right? G of 2 is 9, and then f of 9 is 2, right? So 2 and 9 is like a pair. So g prime of 2 is going to be equal to 1 over f prime of 9. And then you can look here, f prime of 9 is 1/12. So this is going to be 1 over 1/12, which is 12. And that's our answer for question 3. Okay, so next up we have a related rates problem. And the problem is a person is 500 feet away from the launching point of a balloon. The balloon is coming down at 15 feet per second, and we're trying to find the rate of change of the angle of elevation at 200 feet above the ground. Okay, so the first step in any related rates problem is to draw a diagram. So we have a person who is 500 feet away from the launching point of the balloon. This is the launching point. And then we have the balloon here. It is coming down at 15 feet per second. And then we're trying to find the rate of change of the angle when the balloon is 200 feet above the ground, right? So we want to find at this point, we want to find the rate of change when this distance here is 200. Okay, so the next step is to make a list of everything we know. So we know that, first of all, if we're calling this like a right triangle here where this is x and this is y and this is h, we know x is 500, we know y is 200, and we know that the hot air balloon is coming down at a rate of 15 feet per second. So this is the derivative of its horizontal position, right? So dy dt is negative 15 feet per second, and it's negative because it's coming down. And then we also, even though it's not explicitly given to us, we know theta, because theta is the inverse tangent of this over this. The inverse tangent 2/5. Okay? And then we want to find, we want to find the rate of change of the angle of elevation. So we want to find d theta dt. Okay? So our next step is going to be writing an equation that's relating the two variables. So in our case, that equation is going to be tangent of theta is y over x, right? We're relating these two, and we also have the variable we want to find. Okay? And so what I can do now is I can say, alright, well, x is not really a variable here, because no matter what's going on with the angle of elevation and the height, x is always 500. So I can just replace this with a solid 500, right? I'll rewrite that. Tangent theta is equal to y over 500. And then now I can take the derivative of both sides. So the derivative of tangent is secant squared. And then I'm going to multiply by d theta dt, because we're differentiating with respect to theta, not with respect to t. And this is going to be equal to 1 over 500 times dy dt. Okay, and again, we know dy dt, we know secant squared of theta because we know theta, so we can just solve this equation for d theta dt. So d theta dt is going to be 1 over 500 dy dt times 1 over secant square theta, which is negative 15 over 500, because I just replaced dy dt with negative 15, because remember up here, times, and then secant is 1 over cosine, so 1 over secant is just cosine. So 1 over secant squared is going to be cosine squared of theta. Now let's pull up our calculator, and then we want to find theta, right? So theta is going to be the inverse tangent, of 2/5, and that's going to be equal to that number. I'm going to store this in as a variable so we can use it later. Okay, and then so this is going to be negative, stop a bit, negative 15 over 500 times cosine of times cosine of theta squared, and that gets us this right here, which is negative 0. What was it? 2586. 2586, and then the units are going to be the units for theta, which are radians, divided by the units for time, which are seconds. So there's our answer, and this is the, remember what this really is. This is the change of the angle of elevation at y equals 200 feet. Okay, so we're done with this question. Okay, so in this question, we are using local linear approximation to approximate the inverse tangent of 0.98. And so what we want to do first is we want to compare this to, we want to find a value that's close to 0.98 that we know the inverse tangent of. And a pretty clear choice here is 1. I know that the inverse tangent of 1 in the bounds of the inverse tangent function is pi over 4. Okay, so that's our first step. And remember, we want to write a linear equation. So we're going to, and using point slope form, the formula for a linear equation is y minus y1 is equal to m times x minus x1, right? And so this gives us a point that we can use for the inverse tangent function. The point is 1 comma pi over 4. So I can plug this into my point slope form. I can get y minus pi over 4 is equal to m times x minus 1. And then now I just need to find my slope, m, right? And when you think of slope in calculus, you should think of derivatives. So we're going to first take the derivative of the inverse tangent function, and then we're going to evaluate it at our x value, at x equals 1. That's going to give us our slope at x equals 1, right? which is what we want here. So the derivative of the inverse tangent in general is 1 over 1 plus x squared. And remember, we're evaluating this at x equals 1. So this is going to be equal to 1 over 1 plus 1 squared, which is 1/2. Right, and this is my slope at x equals 1. Right, so now I can go back and I can finish writing my equation. Y minus pi over 4 is equal to 1/2 times x minus 1. Okay, so once you've done this, you're pretty much there. You're almost at your answer. So we want to use this to approximate the inverse tangent of 0.98. So I want to take this equation, this x value here, and plug it into my equation. So y minus pi over 4 is equal to 1/2 times 0.98 minus 1. And my y value that's going to come out of this is going to be the approximation. So if I can pull up my calculator here, we're going to have 0.98 minus 1 times 1/2 plus pi over 4. And that gets me my approximation of y equals 0.775398163. Let's check. Yeah. And then what we can do now is we can compare this to the actual value of the inverse tangent of 0.98, and we'll see how close we were. And look at that. Look at how close these two numbers are. We don't know the actual inverse tangent, so we used a value that we do know the inverse tangent for. We plugged it into this linear equation, and we got a really, really darn close approximation. I think it's pretty cool. Now let's move on to the next question. Okay, and for this last problem, we're going to evaluate this limit here. So if we try plugging in negative infinity directly into the limit, we're going to get infinity over infinity, which is a indeterminate form. So that means we're allowed to use L'Hopital's rule here. So I can say that this limit, I'm just going to rewrite what we're given in the problem. is equal to, by using L'Hopital's rule, the limit as x approaches negative infinity of 2x over negative e to the 1 minus x. And if you're not sure what I did there, I took the derivative of this using the power rule, and I took the derivative of this using the chain rule. And so if I try plugging in negative infinity here, I'm going to get negative infinity over negative infinity, which is another indeterminate form. So that means I'm allowed to use L'Hopital's rule again. So this limit that I have here, 2x over negative e to the 1 minus x, it's from right over here, is going to be equal to, again I'm going to use L'Hopital's rule because I still have an indeterminate form, the limit as x approaches negative infinity of 2 over e to the 1 minus x. And if I try plugging in negative infinity here, I'm going to get 2 over infinity, which is 0. So that is the answer to the limit. I'm just going to restate what we just said. The limit as x approaches negative infinity of x squared over e to the 1 minus x is equal to 0. So we just used L'Hopital's rule twice, and the limit that we got is still the answer to the original limit. And so the point of this problem, I wanted to make sure that you understand that you can use L'Hopital's rule multiple times. If it doesn't work once, don't give up, especially since we have a polynomial here in the top. That's eventually just going to get simpler and simpler until it just goes to a number. So you can use L'Hopital's rule multiple times and you'll still be valid, as long as you have an indeterminate form after each step. Okay, so that was the end of the video for this unit, so I'll see you in the next unit. Goodbye.